Pythagoras wasn't much of a mathematician. He was more interested in spiritual matters. Essentially, he was a cult leader. He spent some time traveling, learning, gathering followers before settling in southern Italy. To join this commune near the town of Crotone, a potential pledge would swear a vow of silence for 5 years before they could even meet Pythagoras, this charismatic leader who was rumored to talk to animals and have a golden thigh. The initiate would give up their worldly possessions as everything was shared by the members of the school. Their meals were communal, Spartan style. Everyone followed a plant-based diet that prohibited fava beans. All Pythagoreans shared a belief in an immortal soul. Once the mortal body was broken, the immortal soul would find a new vessel. Human souls would often reincarnate into bean plants, and that is why they were sacred. That's one of the topics Pythagoreans would discuss in the semicircle. Another topic might be the correct way to put on sandals. Right first, then left. Starting with the left sandal was forbidden. Besides beans, Pythagoreans venerated some mathematical objects. There was a triangle with a point in the center and 4 points on each edge. Numbers were not seen as just tools, they were magical objects with their own symbolic properties. Sequence 1, 2, 3, 4 was important. Number 1 was the basis of the numeric world, as every whole number could be made by adding enough ones, and everything could be represented by whole numbers or ratios of whole numbers. Similarly, number 4 represented the physical world, as to their understanding, everything in our world was made from some combination of the 4 elements. I suspect that the reason why we associate Pythagoras with mathematics is not because of his contribution to the field, but because he was influential in his time, and his followers kept promoting him even after he was gone, like a celebrity that is famous for being famous. If we were looking for an ancient Greek philosopher that significantly contributed to mathematics and geometry, a strong candidate would be Euclid. While the name Euclides could be translated as well-known, that name is pretty much all that we know about him. Details about his life have not been preserved, but copies of his work have survived. Perhaps the best known is the Elements. In the Elements, Euclid starts with 5 postulates, 5 simple ideas like one straight line can be drawn between 2 points, circle has a center point and a radius, all right angles are the same, parallel lines will never meet. Then Euclid built up rules and techniques of geometry out of these 5 postulates. If an idea leads to contradiction or a disagreement with one of the postulates, then that idea is not part of Euclidean geometry. Euclid's Elements remained a fundamental text of Western mathematics for 2000 years. In our times, it is said that the only time Isaac Newton laughed is when someone asked, why should they read Euclid? The idea of being able to get anywhere without the fundamentals is hilariously ridiculous. You might not think of Newton as being our contemporary, but a few centuries is not that long into millennia. Euclid and Pythagoras lived centuries apart. Isaac Newton is another character, like Pythagoras, that is associated with mathematics, while a lot of their output is concerned with more spiritual matters. For example, traditionally, the rainbow has 7 colors because Newton felt that the number 7 is special, sacred. It's the number of notes in a musical scale, so he felt that white light should also be split into 7 components. While Newton did contribute a lot to several fields of natural philosophy, if we are looking for prolific mathematicians of our times, then names like Euler and Gauss might come up. Gauss worked on something called non-Euclidean geometry. Almost a century later, writer H.P. Lovecraft would use terms like cyclopean architecture and non-Euclidean geometry as a shorthand for something otherworldly or mind-breakingly incomprehensible. What is non-Euclidean geometry? Well, one example is geometry on a sphere. For example, on a flat sheet of paper, if you note the length of 2 edges and the angle between them, you can work out the length of the third edge of this triangle. Only one line can be drawn between 2 fixed points. If the angle is 90 degrees, then the longer edge multiplied by itself will be equal to the sum of the shorter lengths multiplied by themselves. This rule holds whether the edges are 1 meter long or 10,000 kilometers long. Except that the rule doesn't hold. You see, we live on a essentially spherical Earth. By original definition, 10,000 kilometers is the distance from the North Pole to the equator. If we start at the pole, go 10,000 kilometers to the equator, turn 90 degrees, go along the equator for 10,000 kilometers, there is only one line that will connect the new point back to the pole. And what we have constructed is a triangle with equal sides where every angle is right angle. The reason geometry on a sphere is called non-Euclidean geometry is because it contradicts one of Euclid's postulates. Most of them actually still hold. This geometry complies with Euclid's definition of straight lines, circles, and right angles. It's the fifth postulate that breaks down, the one that says that parallel lines will always be parallel. On a globe, all lines of longitude are parallel at the equator and meet up at the poles. This is called elliptic geometry. If parallel lines stay parallel, then we call it Euclidean geometry. There's also something called hyperbolic geometry, where parallel lines diverge, get further and further away from each other. When I was young, Pythagorean theorem was something we had to memorize. In popular fiction, knowing Pythagoras is a shorthand for a smart character, like memorizing digits of pi or playing chess. This puts the Pythagorean formula a squared plus b squared equals c squared on a kind of pedestal, like it's something special. It's not, although it is a special case of a more general formula that also has minus 2ab cos theta. Basically, for any triangle, once you know the length of two edges and the angle between them, then there is only one length that the third edge possibly can be. And this is the formula to find that length in Euclidean geometry. Nowadays, you don't have to memorize it, just knowing that it exists, so you can look it up when you need it is enough. For right angle triangles, cos of 90 degrees is 0, so we are left with a squared plus b squared of the Pythagorean theorem. Cos of 60 is a half, which also leaves us with a nice formula. If you have a triangle with two edges of the length 1 and 60 degrees between them, then you can work out the length of the third edge. 1 squared plus 1 squared minus 1 times 1 is 1. Oh yeah, well, you need to also take the square root. Okay, that's just an equilateral triangle. There is an interesting result when edges of a right angle triangle are 1, or just any length as long as they are equal to each other. Often, Pythagorean theorem is presented using actual squares. We should be able to split the c square into two equal a and b squares. What is the smallest whole number could c be, so we get this result? Well, if c is even, then we should be able to split the c square into 4 equal squares, which means the two of these quarter squares can be combined into one of the half squares, a or b. If c is even, then it is not the smallest number for a square that can be split into 2 equal squares. A square can be split into 2 of those c quarter squares. If a is even, then it's not the smallest, because we can use the trick we just did on c to create a smaller square that can be split into 2 equal squares. So the smallest value for c has to be odd. Well, no, that doesn't work either, because if the edge of a square is odd, when you split it into 2, it will always leave one remainder that doesn't belong to either half. Basically, you can't construct a right angle triangle with 2 equal sides using whole numbers. If you can measure the size of a square, then you can't measure its diagonal no matter how fine you make the ruler. It's not a physical property. The number itself cannot be expressed by fractions. You will always find that you always need to add another smaller fraction. Story goes that a student of Pythagoras showed this result of Pythagorean theorem to Pythagoras, and Pythagoras' reaction wasn't positive. 1 is sacred because it's a fundamental particle of all numbers. Everything can be represented as a whole number or a ratio between two whole numbers. There cannot be numbers that are just never-ending sum of smaller and smaller fraction. Understandably, Pythagoras ordered the student to be drowned. Stories like this did not endear the locals to this strange vegetarian cult. A conflict between Pythagoreans and the local town of Croton over a democratic constitution led to the commune being burned down by the locals. Pythagoras escaped and he might have reached safety, but then his path was crossed by a field of fava beans. His beliefs prohibited him from stepping on the beans, so he stopped. Not long after, locals caught up to Pythagoras and, according to his beliefs, his immortal soul left his body and reincarnated into a nearby bean plant.